Hey everyone, we're going to dive into 8.5. So switching gears here a little bit, we're going to look at complex numbers and specifically the trig form of complex numbers. You've seen complex numbers in algebra. If you want to review that a little bit, go back to things of the form a plus bi. Remember what I is. I is the square root of -1, right? So these are called complex numbers. There's an imaginary part and a real part, right? So the b is the imaginary part attached to the I, and a is the real part. Turns out it's useful, and there's some applications if you can graph these. In order to graph them, you think of things in a little bit of a different way. The horizontal axis are real numbers, so that's the real axis. And then the vertical axis are imaginary numbers, or the imaginary part. So that's the imaginary axis. And then any complex number of the form a plus bi can be graphed like a vector. So you'll see that this section, there are a lot of similarities to the vector sections, which is kind of cool. So here's an example of, say, 2 minus 3i. Notice how that's graphed. You have a vector where the real part is 2, so that's labeled on the real axis, and the imaginary part -3, that's labeled on the imaginary axis, and then it's a vector starting at the origin going out to that point, 2 comma -3. Okay, so you can practice a little bit with just graphing complex numbers. So like if you had -1 plus 2i, you would just put a set of axes. And you can sometimes you see them labeled as I and R, right? And then the the real part is -1, and imaginary part +2, and then you would just do a vector out to that point. Okay, so starting at the origin, going out to that point, right? And that would be the graph of it. Okay, so that's it. It's a lot like, it is like vectors, right? So it's kind of like we've done this before, it feels like. How about 5i? So if I just set up my axes, imaginary, real, since there's an I attached to it, but this one there's no real part, so that'd be at 0, but imaginary I'd go +5, so up 5, 1, 2, 3, 4, 5, right? And then it would just be on that axis. If I did the actual vector, stop at 5, like that. So look, and then number 3, -4, that doesn't have an I on it, so that's going to be on the real part, real axis. So we got real, imaginary, -4, so that's going to be in the negative direction, out to -4 out there. And then do your vector starting, it always starts at the origin and goes out to the point. So it looks something like that. Okay. The nice thing is when you add complex numbers, it's a lot like adding vectors, right? I mean, the picture's identical and the algebra is the same too. So it's all the same. So if I'm going to add these together, I'm going to add the real parts together, the 4 and the 1, and then the imaginary parts. Right? So just add like terms, really, right? That's 5 plus 4i. Just like the picture shows, that parallelogram law from vectors. Neato. Okay, and then there's a relationship among, if we take it back to x and y and r and theta, right? So that picture is just the trigonometric relationships among those variables. Now we're using x and y here in this one as so x is your real part and the y is the imaginary part. Okay, and then the r is the magnitude or the length of that vector, and theta is the direction angle. Okay, if you do it in that way, you end up with what's called the trigonometric form of a complex number, and it's right here. right? And if you're wondering where that comes from, it's really just that triangle, right? Like if you try to come up with a formula for x, well, I could just use right triangle trigonometry. Cosine of theta is x over r. So x is equal to r cosine theta, right? So I'm replacing x with r cosine theta. Notice r has just been factored out because it's also going to appear with the sine, right? Because sine theta is y over r by that picture. So y is r sine theta. So you're just going to replace the y with r sine theta. And there it is, right? And factor out the r. Okay. So you'll see this as the trigonometric form. There it is. We'll be using that a lot in these next two sections. There's a little abbreviation for it because the angle is always the same, right? With this part and this part, that theta always matches. So you feel like you're writing a lot of repetition. So you'll see this form as an abbreviation. So when you see that CIS, that just means cosine theta plus I sine theta. Okay. So just take it for what it is. And we'll do some examples where we use this, right? We have now two forms of a complex number. We have trigonometric form and rectangular form. Rectangular form is that standard a plus bi. Trigonometric form is this new thing here. And then so here I just put in some directions on how to transfer from one to the other. So we'll refer back to that as we do the examples. So let's jump to some examples. Let's see, how can we convert this thing that's in trigonometric form to a rectangular form and use exact values? Really, it comes down to the unit circle. So get out your unit circle. You probably have that handy somewhere, and just find the cosine of 300 degrees on your unit circle, right? So what is the cosine of 300? You go to your quadrant 4, you look up 300, or maybe you can do this in your head at this point, which would be super awesome. But if you have to look it up, that's okay too. Cosine 300 is 1/2. So we can plug that in to, sorry, that, drop my pen right there. And then the sine of 300 is -√3/2. So plug that in right there. So really I'm just plugging in values, calculations, exact values, unit circle, right? And then I would just distribute the 2, right? So 2 times 1/2 is 1. And then, oops, let's write that as, since this is a minus here, minus, right? The 2's would cancel and I just get √3. So I √3. It's standard to put the I in front of the square root, right? I mean, you could write it like this too. Doesn't really matter, it's multiplication, but sometimes the I is better out front, so it doesn't look like it's inside the radical. So usually that's kind of bad form. So typically you'll put the I in front of radicals. Okay. Next, how about this one? Okay, now, I mean, hey, if you know how to do unit circle, you get these right every time. Cosine of 180 is -1. Sine of 180 is 0. Right? And so this is really just 4 times -1. That's -4. Right? A real number. So this is just a real fancy way of writing -4. Okay, which does come in handy, right? So we're not doing this for no reason, but trig form, as we'll see, has some nice applications later. And here's one where you won't use the unit circle, you have to use a calculator. So because that 157 degrees is not on the unit circle. So I'm just gonna take out my calculator, make sure I'm in degree mode, and just calculate cosine of 157. Let's take this out a few decimal places. 9205 plus I times the sine of 157 is 0.3907. right? So just a straight calculation and then distribute the 3 and you're done, right? So if I times 0.9205 by 3, and then now I'm going to round to what it says nearest hundredth. So that's 2.76. I have negative 2.76. And then plus is a positive. That's going to be 1.17 I. Okay. So if it's a whole, I mean, if it's not a radical 1.17, I put the I behind it. And then we got it. Okay, moving right along. How about converting the other way, convert to trig form? Now these takes a little bit more work. If you have the rectangular form and you want to go to trig form, the steps are probably more helpful there, right? So I think it's helpful to sketch it, right? And then you're going to find R by this formula, and then find theta essentially by that formula. It feels like we've done this before with vectors and kind of have, right? So that's pretty nice. All right, and then you just got to make sure you're in the correct quadrant, and that's really why you graph it or sketch it in the first place, to make sure you got that angle right. Okay, so I've already drawn this one. We are in quadrant 2, right? So that's how the graph will look, right? Again, we're doing imaginary axis and real axis here. And then the first thing I'm going to get is that R, and the R is formula square root negative root 3 squared plus 1 squared. And that I think works out pretty nicely. So that's going to be negative root 3 squared is just 3, right? And 1 squared is 1. So it's the square root of 3 plus 1, which is square root of 4, which is 2. So R is going to be 2 there. Okay. So put that on the back burner for a moment. Now go get the theta. And notice I have 2 labelings. The red theta, that's the one I want. And then there's this theta prime, which is the reference angle. I'm going to get that first. Okay. So remember, for reference angles, just ignore negative values and just do the y over the x. So the y is the coefficient of the I, which is 1. And then the x is the root 3. Okay. So my reference angle is going to be tan inverse of 1 over root 3. Right? And if you calculate that, we get 30 degrees. Okay, that's the angle inside that triangle. Now the red theta, notice, is starting on the positive real axis. So that's, if this is 180 over here, right? I could just do 180 minus my reference angle. So theta, the one I want, the direction angle, is 180 minus 30, or 150. Okay. All right, now I've got my theta and I got the R. Now put those together in that trig form, right? Basically, you're just writing this, right? But just plugging in the R and the theta. Okay. So that's going to be 2 parenthesis cosine 180, 150 plus I sine 150, right? Or if you like that shorter notation, you can just write 2 cis 150. Okay. Either one is acceptable. And that's the trig form. All right. Want to try another one? Negative 3i. This one is, if they end up right on an axis, they're actually a little faster, right? Because notice here, R is the distance on that axis. So since we have 3, we're going down 3 units, I just can tell that R is 3, and R is always positive, right? Now you could use the formula too, x squared plus y squared square root, it would still give you 3, or at least you can just do the shortcut and just look at it, okay? So if you want to verify that formula also works, you'll get R is equal to 3. And then also from the picture, I get theta, the red theta goes all the way around to, that's 270 degrees. I know that from unit circle work, right? Okay, so really it's all about the picture if it ends up on an axis. And I'll backtrack a little bit. Did we get that picture right? So notice my value is -3i. There's no real part. So it's just going to be on the imaginary axis only, and it's -3i, so that's in the negative direction on the imaginary axis, 3 units down. Okay, so I got the graph right as well. Okay, so now put it all together in your trig form, and it's going to be 3 cosine 270 plus I sine 270, right? And if you want to check your work, you can just calculate cosine 270 and sine 270, plug those values in, you should get -3i back. Okay. We got one more. This one has some rounding involved, probably not going to work out all that nicely, right? So we're just going to have to use our calculator. Okay, so there's my picture. I got it in the right quadrant. It's a +4 on the real axis and a -5 on the imaginary axis. Okay, and that's a vector going out to that point, 4, -5. So that looks good. So let's get the r first. R is square root x squared plus y squared, 4 squared plus -5 squared. Right? So that's going to be 16 plus 25, that's square root of 41. And this one does, I mean, sometimes you can just leave it like that, or they, if it says anything about rounding, just go ahead and calculate that. Square root of 41 is 6.4. Okay. Now let's go get that theta. And again, I'm after that theta prime first, that reference angle. So tangent theta is opposite, or the y, which is 5, over the x, which is 4. So theta prime is tan inverse of that, tan inverse of 5 over 4. And let's get the calculator going on that. 5 over 4. I'm getting 51.3 degrees. And that's my reference angle. So for theta, let's see, how could I get theta here? It's in quadrant 4. The full revolution is 360. So it's 51.3 degrees short of 360, or 360 minus 51.3. Okay, and calculate that out. 360 minus 51.3. That's 308.7. Okay. And now put it all together. So let's see, we got the r out front, cosine of 308.7 plus I sine 308.7. Or you can do that cis thing if you want, but there's my final answer, and feeling pretty good about that. Okay, we can probably knock out this whole note packet right now. Let's do it. So how about the product of a couple of complex numbers? There's a formula for it. It looks kind of long. You're like, whoa, that's crazy. But really all you're doing, if you have two complex numbers, this one and this one, you multiply the r's together and you add the angles together. Okay, and then you simplify. That's it. So this formula comes from, by the way, addition and subtraction identities from chapter 7. Like if I wanted to prove this, I would go over here and I would FOIL, right? Multiply outsides, insides, do the whole FOIL thing, and then simplify with addition identities. So if you're curious about proving that, give it a try. It's in the textbook as well. And there's something similar for the division, the quotient one. Notice in the quotient one, you just divide the r's and you subtract the angles. Okay, so as intimidating as those formulas look, the function of them is pretty straightforward, actually. Like if I look at an example, number 11, so if I'm going to multiply these two together, I'm going to multiply the r's together, right? And then I'm going to do the cis thing, right? Because it's just kind of a nicer way to write it out. And I just add the angles, the 45 plus the 135. Right? Okay, so that's it. Remember what cis stands for. It's cosine of those two angles added together, right? Plus I sine of those two angles added together. So what I'm really doing here is I'm just thinking of this as cis theta 1 plus theta 2, right? Theta 1 is there, theta 2 is over there. That's theta. There's two theta 1s and there's two theta 2s, okay? Okay, so this is going to be 3.2 cis. If I add those together, that's a nice 180. Hey, that's not 3.2. Sorry, that's 6. I fooled myself, didn't I? With my bad handwriting. Okay, that's 3 times 2 out there, which is 6. 6 cis 180. Okay. Now it says it wants in a rectangular form, so I got to keep going here, get it that rectangular form. Really, the cis just means cosine 180, I sine 180, right? I mean, if you prefer to write it like that, you can. So, or you can just think of it like this, right? So really what you need is the cosine of 180 and the sine of 180 from your unit circle. Cosine 180 negative 1, sine 180 is 0, right? Going back to beginning of the semester, really, right? And so this is really 6 times negative 1, negative 6. That's pretty crazy. So those two things multiplied together is equal to negative 6. Guess we just got to buy that, right? How about a quotient one? This one already gives us that cis form. So just remember what that means, cosine, I sine. Right? So on these, you divide the r's and subtract the angles. So negative 60 minus 150, right? So I'm just using this formula right here. That's the same as if you like that cis form, right? There's the cis form of it. That's what I'm doing, okay? Okay, so we've got 2 cis negative 210, right? And then to get this in a rectangular form, cis negative 210 means you got to find the cosine of negative 210 and the sine of negative 210. So the cosine of negative 210, go to your unit circle, negative 210 is the same place as positive 150, right? And at that positive 160, you'll see that the cosine is negative root 3 over 2. Plus, and then the sine is positive 1/2. So I'm going to do I times 1/2. Okay. And then finally distribute, and we should have our final answer. So the 2's are basically going to cancel. We're going to get negative root 3 plus I. That's the rectangular form, the answer. Might seem pretty bizarre, like what are we doing? But kind of cool too, in a mathy sort of way. So spend some time with it. You just got to get used to the notation really. And then the actual work is not too bad. Okay, that's it for 8.5. Send questions my way if you have any. Hope all's well. Bye.